Fog looks simple, a white wall that appears out of nowhere. It hides landscapes, disrupts traffic, and turns ordinary places into something mysterious. But fog is not random. It is the result of a very precise physical process that occurs only when the atmosphere reaches a specific thermodynamic limit. That limit is called the dew point. The air around us is not just oxygen and nitrogen. It always contains water vapor, invisible water in its gaseous state. Warm air can hold more water vapor than cold air. This is not just a rule of thumb, it is a direct consequence of molecular energy and vapor pressure dynamics. As air cools, its capacity to hold water vapor decreases. At some temperature, the air becomes fully saturated. This is the dew point temperature. If the air cools even slightly below this threshold, the excess water vapor has nowhere to go in gaseous form. If you like similar educational content, please like, subscribe, and share the video with your friends. But fog does not form because water suddenly appears. The water was already present. What changes is its phase. Individual water molecules begin clustering together into microscopic droplets. These droplets are typically between 10 and 20 micrometers in diameter. They are small enough to remain suspended in the air, but large enough to scatter visible light. And it is this scattering of light that makes fog visible. Without light scattering, fog would be invisible. But there is another crucial ingredient: condensation nuclei. Water vapor does not easily condense in perfectly clean air. It needs microscopic particles, dust, salt, smoke, pollen, to serve as surfaces where droplets can begin forming. These particles act as condensation seeds. Without them, the air could become supersaturated without immediate fog formation. Fog is therefore not just cloud at ground level. It is a delicate balance between air temperature, relative humidity, atmospheric stability, presence of microscopic particles, air movement. If any of these variables shift, fog may not form or may quickly disappear. So why does fog often appear at dawn? Why is it common near lakes and valleys? Why does it sometimes last for hours, while other times it vanishes within minutes? To answer these questions, we need to understand the relationship between temperature, relative humidity, and dew point in greater depth. To truly understand fog formation, we must examine the thermodynamic relationship between temperature and water vapor capacity. Air does not have a fixed ability to hold water vapor. Its capacity changes continuously with temperature. The warmer the air, the higher its saturation vapor pressure. This means warm air can contain significantly more water vapor before reaching saturation. Relative humidity measures how close the air is to saturation. It is not the total amount of water vapor present, but the percentage of maximum capacity at a given temperature. For example, air at 20 degrees Celsius can hold far more water vapor than air at 5 degrees Celsius. If both contain the same amount of water vapor, the cooler air will have a much higher relative humidity. When relative humidity reaches 100%, the air becomes saturated. The temperature at which this occurs is the dew point temperature. If air cools to its dew point, condensation begins. This is why fog commonly forms overnight. During clear nights, the ground loses heat through infrared radiation into space. As the ground cools, the air in direct contact with it also cools. If this cooling continues until the air temperature equals the dew point, condensation begins near the surface. But cooling alone is not enough. The atmosphere must also be relatively stable. Strong winds mix air layers and prevent local saturation. Fog formation is therefore most common under calm conditions. Condensation also requires microscopic particles. These condensation nuclei provide surfaces around which water droplets can form. Without them, air could become supersaturated without immediate droplet formation. The droplets that make up fog are extremely small. Because of their small mass, they fall very slowly. Air resistance and minor upward air motions keep them suspended. This is why fog appears to hang in the air rather than fall like rain. At this stage, fog formation depends on a delicate equilibrium, cooling rate, initial humidity level, air movement, surface conditions, particle concentration. Even small changes in any of these factors can determine whether fog forms or not. Although the physical mechanism behind fog formation is always condensation of water vapor, the pathway to saturation can differ significantly. These different mechanisms produce distinct types of fog, each with its own behavior and duration. The most common type is radiation fog. Radiation fog forms during clear nights when the ground rapidly loses heat through infrared radiation. As the surface cools, the air directly above it also cools. If the temperature drops to the dew point, condensation begins near the ground. Radiation fog is typically shallow and most common in valleys and low-lying areas where cold air can accumulate. It often forms in the early morning hours and dissipates shortly after sunrise when solar heating raises the temperature above the dew point. A very different mechanism produces advection fog. Advection fog forms when warm, moist air moves horizontally over a colder surface, such as a cold ocean current or a cooled landmass. The lower layer of air cools from below. If it reaches the dew point, fog develops. Unlike radiation fog, advection fog can persist throughout the day because it depends on continuous air movement rather than nighttime cooling. Coastal regions frequently experience advection fog due to ocean temperature contrasts. In mountainous terrain, orographic fog can develop. When air is forced upward along a mountain slope, it expands due to decreasing pressure and cools adiabatically. If the cooling is sufficient to reach saturation, fog or low cloud forms along the slope. In many cases, what hikers experience as mountain fog is simply cloud formation at ground level. Another interesting type is evaporation fog, sometimes called steam fog. This occurs when cold air moves over relatively warm water. Evaporation from the water surface increases humidity in the lower air layer. Because the air is cold, it quickly reaches saturation, and condensation occurs. This type of fog is common over lakes in autumn and early winter. Each type of fog results from a different combination of cooling from below, horizontal air movement, vertical lifting, temperature contrasts, moisture input. The physics of condensation remains the same, but the atmospheric dynamics vary. The boundary between fog and low cloud is primarily altitude-based. If condensation occurs at ground level, we call it fog. If it occurs slightly above the surface, we call it stratus cloud. Reaching the dew point does not automatically produce thick, opaque fog. The density of fog depends on the concentration of droplets and how efficiently they scatter light. Each microscopic droplet acts as a tiny optical scatterer. When sunlight or artificial light enters fog, it is repeatedly scattered in different directions. The more droplets per unit volume, the stronger the scattering effect. As scattering increases, contrast decreases and visibility drops dramatically. Interestingly, the total amount of water in fog is relatively small. Even dense fog contains only a few grams of liquid water per cubic meter of air. What makes fog appear thick is not the quantity of water, but the distribution of that water into millions of suspended droplets. Fog dissipates when the balance that created it shifts. This can happen through an increase in air temperature above the dew point, a decrease in relative humidity, stronger wind mixing dry air into the saturated layer, solar heating of the surface, arrival of a different air mass. As soon as relative humidity falls below saturation, droplets begin to evaporate. The transition can be surprisingly rapid. Within minutes, dense fog can transform into clear air if sufficient warming or mixing occurs. Fog plays an important role in transportation safety. Reduced visibility affects road traffic, aviation, and maritime navigation. Modern aircraft rely on instrument landing systems when fog reduces visibility below safe thresholds. From a climatic perspective, fog modifies the surface energy balance. During daytime, it reflects incoming solar radiation, limiting surface heating. At night, it can reduce radiative cooling by trapping outgoing infrared radiation. In this sense, fog can act as a temporary insulating layer. In certain ecosystems, fog provides a significant source of moisture. In arid coastal regions, plants capture water from fog droplets deposited on leaves and surfaces. This process can sustain vegetation where rainfall is limited. Ultimately, fog is not mysterious. It is the visible result of air reaching thermodynamic saturation. When temperature, humidity, atmospheric stability, and particle concentration align, invisible vapor transforms into a suspended cloud at ground level. Fog is simply the atmosphere crossing a physical threshold between gas and liquid and revealing that transition to our eyes.